Let's walk through a critique of two lab reports and note the things which work and the things which need improvement.
This is Lab 9, and today we'll be looking at a spring in constant motion moving from side to side. Basically, we'll be obtaining the oscillation.
Now there's an obvious problem here. The video is sideways. This shot was probably taken with a smartphone camera held vertically, pointed at a piece of paper held vertically, but with the camera set to landscape mode. If you want to show text, you can type it directly into our video editor as a subtitle or title, like this. Or make sure your writing and your camera are horizontally oriented. Subtitles are a great idea if you don't have the neatest handwriting. This part of the video is intended to show the viewer the setup of the experiment, and it mostly works, but there are a few difficulties.
Get our experimental data, which we use to compare, and as you see, we have it set up as a normal system. Lengths and all of that is specified.
First, the footage is blurry. This would be better if it were taken as a screen recording and not as a recording from a smartphone. In terms of physics content, there's too much glossing over of important issues. The speaker says, "We have this set up as a normal system," but doesn't say what that really means. The speaker also says, "Lengths and all that are specified," but that's pretty vague too. We can see he has a blue tracker calibration stick set to the initial length of the spring, and that the origin is located where the spring connects to the stand, and that the positive x-axis points to the right. A good way to state all this important information and still save valuable time is to show the information clearly in writing without verbalizing it. This lab report also has audio problems.
Over time, which one could use to calculate the time period. After viewing data from the tracker, we can now look at our data extracted using Vital. As we can see, we have the X.
There's a rustling noise, and suddenly his voice gets a lot louder and clearer. It appears that he was holding his phone and blocking the microphone with his fingers, and then readjusted his grip to unblock the microphone. He should have gone back to reshoot the muffled footage. If you notice an error like this, you should reshoot too. That's why it's always best to take a few seconds of test footage before committing to a whole take.
627, 1 point, yeah, and you see time period for Y. As you can see, we have the Y1 on the bottom right there. As you see, the red line once again representing the same thing. This one's a little bit off, but it's pretty precise measurement for the oscillation back and forth for.
The data generated from this speaker's simulation looks okay in one direction, the X direction, but not the other, the Y direction. By looks okay, we mean that the predicted position in red is close to the observed position in green. There's a serious discrepancy between the predicted and observed Y position. The simulated mass only has about a third of the range of motion in the Y direction as the observed mass, which suggests a problem with the model. At one point, the speaker does point to this discrepancy, which is good practice, but the speaker tries to pass it off by saying it's a little bit off, but it's a pretty precise measurement for the oscillation. Well, it isn't a little bit off, it's way off. Don't try to hide mistakes or difficulties in comparing your model to your observations. Point them out explicitly. That's how we do good science and how we start good conversations about physics. It also makes for better video lab reports. In sum, this video lab report has several technical difficulties and a few serious errors in content. We'll say more about the content errors later in the course, but for now, a good lesson for us to take away is to recognize that this video report could have been greatly improved by just scripting things out ahead of time and reshooting a couple of the shots. Let's now look at another video lab report.
The purpose of this lab is to view the effect of drags on two objects, one experiencing little drag force and the one experiencing strong drag force, and applying the momentum principle to explain what's happening in the video. First, I made observations of a volleyball with the first V Python made with the assumption that the drag force was negligible. Terminal velocity and position were found by these models. This is my clip of the volleyball being dropped.
Short, clear, and to the point. The creator of this video lets us know right up front what her report is about and the fundamental physical principle most important to her analysis. She's also recording directly from her computer screen, so the video is nice and clear. What's good is that she's very clearly stating her assumptions about what's going on physically. That makes her report easy to follow.
The clip starts at the point the volleyball was released, and for now the only force is gravity. The first frame set the origin of the system at the starting center of the mass at time 0, and the negative side of the y-axis is pointing downwards to show the ball is falling. The point masses were in the center of the ball as it was falling, and measurements were calibrated to the length of the ball, which was originally 0.65 meters in the beginning.
Here she clearly lays out her length scale, her decisions about the coordinate system, and the model she's working with. She could stand to be a little more clear about that last part when she says the only force here is gravity. It's not clear here whether she's talking about the experimental system itself or the model she'll soon be using to describe this system. Let's see if she addresses that point later in her analysis.
This is my model based on Newton's second law, which states that an object's acceleration depends on the net force and mass. We're removing the drag force in this case. So their hashtag, and the time is set to 0.5 seconds, and with the mass.
Now she's justified in saying there's no drag, because she's clearly describing her computational model. She explicitly removes the drag force from the model itself, which is not something we generally can do in real life. She does a good job pointing out the relevant lines of code. The important one here was the one where the drag force was commented out. Again, this is recorded directly off her screen, so the text is nice and sharp. The text could stand to be a little larger. You can change this for yourself in your videos in the Preferences menu on VIdle.
The initial velocity is 0, and the only force acting on it in the beginning is gravity. For all the models without drag force, graphs of time versus position show a straight line, because with gravity being the only force, the velocity will be constant due to Newton's first law of constant force means constant velocity. Drag force is proportional to object's velocity and surface area perpendicular to the direction of motion. Knowing this, the graph of all three, the observed model without drag and model with drag, both experience both gravity and increasing drag curve, with the end of the observation showing a slightly straight line. The net force in the beginning isn't equal to 0 due to constant force of gravity, but acceleration occurs until the drag force right here is equal to the magnitude of gravity acting in the opposite direction. Then the velocity will become constant.
Here she offers a very clear interpretation of the physical goings-on in her model. It's very important to state what you think is happening, even if you're mistaken in your understanding. This student is doing a very good job of stating what she thinks. Because she's clearly stating her views about physics, her peers can respond to them and help her to improve them. This process would be much more difficult for the creator of the first video, because that speaker never clearly explained things in terms of core physics principles.
This is the data of the cup of the observed with the drag and without the drag. The initial velocity is set to 0, and the air resistance being ignored, the velocity is constant, as seen here without the drag. But with the model of the cup with the drag force, it curves, showing that there's a net force not equal to 0. The observed is much different from the models because the model doesn't account for the surface area or the shape of the cup.
Here we have some models which predict motion that is very different from the observed motion of the object. The student makes note of this difference and tries to explain it. This is good. The explanation itself is a bit lacking for reasons we'll discuss later, but she made a definite assertion that can be addressed, discussed, and improved. Let this be a guideline for your reports. even if you're not entirely sure you understand what's going on physically. You'll find these videos and several others like them in the forums. I encourage you to discuss them with your course mates, paying attention to both the technical quality of the videos and the physics content within them. We're looking forward to some excellent video lab reports coming out of our course soon.